Welcome to AI driven perception, learning, mapping for drones. Lecture 2, Foundation in Neural Networks, Basic Concepts. In the last lecture, we talked about how why we need AI for different application of the drones, swarm drones and future concepts and all that. This particular module focused more on foundations of neural networks, basic concepts on perceptron, why perceptron, how we can use different learning algorithm, history of learning, evolution, all this we will cover. Let's try to look at the learning objective for this particular lecture. We talk about foundations, right? We introduce students on definition of important concepts. In continuation with the previous lectures, some terminology we introduced, we recap again. Different type of neural network architecture, history of learning, taxonomy of learning paradigms, right? We look at data preparation for learning, real world application. Those are the focus of this particular lecture, okay? And of course, at the end, we'll summarize with respect to different metrics which will be used for general task in shallow neural networks. This will be applicable across the entire module. Now let's look at the terminology just to give a recap with respect to what we discussed in the last lecture too. What is AI? AI is a simulation of human intelligence processed by computer system. It talks about learning and how it can improve its performance by experience. Talk about reasoning, how it can draw conclusions. It can talk about perception, understand the scene using multimodal sensors like camera, LiDAR, event camera, depth camera and multispectral camera, how it can understand the scene from the multimodal perceptions. And it can solve complex problems by dividing the task into multiple subtasks and execute them in sequentially or simultaneously so that the complex task can be solved with the objective either minimum time or maximum success. Like that, the task could be defined that can be executed, right? Language and understanding, it has to read, write, converse in human language and understand the emotions attached with the human language and understand the context in the scene and interpret better. Of course, we talked about machine learning. Machine learning is a computer system, learns from the data to improve the performance without being programmed for a specific rule. Right. Here data is not the raw data. Here data consists of extracted features so that the computer can learn from the extracted features. Right. Finding the pattern in the data and predict the outcome of the new data is the focus for machine learning. When we talk about deep learning, it's artificial neural network with many layers. They can learn complex patterns from the data. It can extract these features. Feature learning is part of it, right? Let's look at in a way to understand them better. Artificial neural networks has many layers, as I mentioned. It has a building blocks. Building blocks come from neuron. Neuron is a basic unit. In this particular module, we look at how we can model this neuron, how it processes the signal, how it activates the next neuron, and how we can modify these activation aspects of it, what are the different type of activation, all this we will discuss in this particular module. We will also talk about weight. Weight is the strength of activation which is connecting between the input and the neuron. How these weights can be modified to represent the data, can we learn them automatically, all this we will be doing in this particular module. Activation functions, it's a nonlinear function that defines how the neurons behave. We have a discrete function, we have a continuous functions, the different functions are available, why these functions are selected, which one suitable for the problem, we will be discussing in this module in detail. Learning paradigm, of course, how the weights are getting updated. If you have a teacher, you can do it in supervised manner. If there is no teacher, you have to do it unsupervised or reinforcement learning where you have a feedback at the end of the course, you give a credit, that's a feedback, right? So how do you learn when you have a feedback? Those kind of learning paradigms are there. We will be defining all those learning paradigms in this particular lecture itself. There are popular architecture quite often used: shallow neural networks, convolution neural networks, recurrent networks. In recurrent networks you have some variations. Convolution networks are for different applications, and people have come up with different architectures. We'll talk about it, all of this, when it comes to module 2 and module 4. Right? Generative neural network, we have a separate module on that, where we talk about how different generative networks are and how they can be useful for aerial perception and planning. Now let's try to understand this AI and ML. Artificial intelligence, if you look at it as the 5 different aspects of it: learning, perception, understanding, problem solving capability, and perception, right? So this is a bigger umbrella. But if you look at the machine learning, it's one part of it, learning from experience. Whereas if you look at a deep learning, where features are automatically extracted from that, and that you learn even the features and the knowledge simultaneously, right? When teaching the computer to learn a specific task from a raw data is given. From there it extracts some abstract features, right, mid-level features and low-level features, and with all this mid-level and low-level features is trying to get an abstract representation of the pattern present in the raw data, right? And that abstract representation helps to derive the knowledge. When unseen data comes, I will be able to extract the low-level, high-level features and create an abstract representation, and that becomes your feature space, and use the feature space to learn the relationship between input and output data. Now let's look at a feature extraction itself. What do we mean by feature extraction? A process of transforming a raw data into reduced features which describe the distribution completely, right? These features represent most relevant information in the data, and this relevant information helps us to discriminate the output as accurately as possible. For example, if I say I want to identify the car, what are the features that we will be looking at a car without even having an image of the car? You can say a car should have at least 4 wheels, 4 doors, right, 4 windows. If I have all these, then I can just say it's a kind of a car. But the moment I say a train, I am looking at more wheels. Car can go in road, whereas a train can go in particular structure of the road, which is what we call rail. More windows, more compartments, the length is longer, right? So you see, I am trying to extract certain features. This is what I mean, these abstract features that help me to represent the data much better. But extracting this for all, it's a time consuming process, and it's not scalable too, right? So for example, I put a raw data, there is an expert which he sits and identifies, okay, this particular class has these are features, right? Now if I want to differentiate 2 cars, common features like number of wheels, number of doors and number of windows are not going to be sufficient. We may need some special features to discriminate them. What are those features? Can we extract those features accurately? And the cars can be used for different purposes. A vehicle can be used for different purposes. It could be an ambulance car. It could be a government vehicle. How do I differentiate between a government vehicle and a common vehicle? How do I differentiate between a commercial vehicle and a common vehicle? It could be a taxi. The white board and yellow board differentiate it's a commercial vehicle or a normal vehicle. So how do I identify such kind of features? It's going to be really time consuming and not scalable. Once I extract this feature, I can pass on to the network and make the prediction, right? Whereas if I go to deep learning, I'm going to give the raw data. The network going to extract these abstract features in a hierarchical fashion and automatically identify these features and transform them into something, an abstract notion of feature space, which will help us to differentiate the classes more accurately, or it helps us to represent the pattern in the data in much more concise and precise fashion. We will read through that in the subsequent module. At the end of the lecture, you will be able to appreciate what deep learning does, how it minimizes the time consuming non-scalable task of expert, but still we need expert to provide some prior knowledge to help us to identify what is the right data, right. We will talk about all of this in this particular lecture too, right. Now, where is the inspiration comes from the network? Inspiration for artificial neural network comes from human brain. Our brain has lots of neurons. We are interested only in the grey matter. We are not interested in the white matter, right. The combined together it plays a very important role. Different parts of the brain responsible for different information processing capability and decision capability. Your auditory cortex process the sound signal. Your visual cortex process the visual signal coming from eye. Your motor cortex, it provides an actuation signal to your muscles to perform something, right. And this complex brains are highly interconnected. The neurons in the brains are highly interconnected and massively parallel. Even though they process the data very slowly, they can process a complex information much more faster and more efficiently because of the massive parallelism exists in the brain, right. There's highly parallel, highly interconnected neurons that helps us to process the information and store the information much more efficiently. That is why we call humans are pattern seeking animals, right. Close to 10 power 11 interconnected neurons are present in our brain, and approximately 10 power 4 connections for every neuron. So it gets data from multiple neurons and process this information, and that is how we are able to process the data much more faster and efficient. Typically the processing speed in the brain is about milliseconds, which is much slower when compared to a modern day computer what we have, which we process in microseconds, sometimes even nanoseconds. But the massive parallelism, massive interconnections that it has, it helps to process the data much more efficiently than the modern day computer. High parallel processing capability, right. Simultaneously I can process the data in multiple neurons and then represent it. That is the thing, the distributed representation that will help in fault tolerance. One neuron dies, no information is lost. Someone is already storing the data in different locations that get activated, right. The resilience aspect is naturally present in our human brain. Some of the key properties of the human brain which we need to really look at it when we are developing artificial neural network. Adaptability, it has a self-organizing capability to reorganize the information, it has ability to generalize the information on different scene. It is not like I have to, you go to a driving school, you learn that learn to drive a car in a village, still you can drive a car in a city or even in highways. You have fast adaptability, you are able to generalize various aspects of relationship between the speed and the distance, apply it, the context of changing rules, right. The speed limit at the different roads are different, the traffic conditions are different, you are able to adapt and control your driving such that you do not have to have any, you reach the goal very fast and without any accidents, right. High reliable transfer from one point to another point. Fault tolerance, ability to adapt other neurons so that the informations are not lost. These are some of the key characteristics that we want to have in our artificial neural network, in addition to the massive connectionism and ability to process the information with different neurons. What is then artificial neural network? If I have to define, an artificial neural network is a massively parallel distributed processor made up of simple processing unit that has ability to store knowledge. Knowledge are stored in the form of weights, and these knowledge is acquired by the network from the data through the learning process. The learning algorithm, what we mean, is the process by which we extract knowledge from the data and represent that the knowledge in a synaptic weight. A synaptic weight, when we say, is a weight between two neurons, the strength, interneuron strength that used to store the knowledge, right. So, automatically the network extract the knowledge and store the knowledge in the synaptic weight. What are the properties and what are its capabilities? Nonlinearity, a network made up of interconnected nonlinear neurons, right. This nonlinearity helps us to represent such a complex relationship more efficiently. For example, when you have seen your friend after 7-8 years, your brain is capable of understanding the growth that one will have when the age progresses and attach those information to your earlier information about your friend, interpolate them and predict this is how he will look like. This is how the voice might have been changed, right, and requires that nonlinear complex relationship it is able to extract and store. It has the ability to store the input-output mapping. The interconnected weights and nonlinear neurons represent such a complex relationship I talked about between the input and output. Your input is the image, output is what you want to predict is your friend, right, or input is an audio, you wanted to say that, oh, it's my friend, a school friend, I am going to see him after, I am hearing him after so many years, voice might have changed, right. So, that ability to adapt, even there is a small variations in his voice now, the ability of the network to adapt the variations in the synaptic weight to handle the changes that happen in between input-output relationship. The fault tolerant ability, if one neuron or one synaptic weight corrupts, the performance does not degrade. So, we need to bring in that kind of a fault tolerant capability such that the interconnected neurons store the data in distributed fashion. One synaptic weight does not affect the performance of the entire network. So, we need to have a distributed nature of the network. There are different type of neural networks available. One what we call feed-forward neural network, where the input goes from one layer to another layer, right. So, here you can see the network goes from, if you look at that, there is an input vector, it goes from input layer to one hidden layer. I could have thousands of hidden layers, I am just showing it with a single hidden layer so that you can appreciate the data flows from input layer to hidden layer to output layer, only forward direction the data goes for processing. If you look at a feedback neural network, you have input layer, you have hidden layer, the output of the hidden layer is delayed and sent back to the input layer, which means there is a feedback connections from output to input. These kind of neural networks are useful for prediction in temporal prediction, time series prediction, forecasting kind of a thing. Now, let us look at the difference between feed forward and feedback neural network architectures. First, let us look at what a feed forward neural network is. Information flow in one direction. When I say one direction, input, hidden layer 1, layer 2, layer 3, layer 4, layer 5, all the way to output layer, one directional flow. There is no memory here. See, do not confuse between memory and knowledge. Knowledge is the information that I extracting from the input output relationship and store it in the weight. When I say memory, memory means I am feeding some information from hidden layer to the input layer. What was my earlier output? Can I use the earlier output also along with the current input to predict, right? That's what I meant. It's very simple, fast and easy to train. It's been used for tasks like classification, regression problem, right? Predicting the nonlinear relationship between input and output. For example, when you say my aerofoil is there, I wanted to know what will be the lift for a different angle of attack and velocity, and the aerofoil is not highly nonlinear. I just want, instead of using table lookup, can I have a neural network? I give the angle of attack and give the velocity, it should give me the lift, right? Unknown information, I can predict it for the current observation. On the other hand, if you look at a feedback neural network, they have a cycle, right? They are not, information doesn't flow in one direction, they go in a cycle. Some layers feed back to itself, or it can feed back to the previous layer. There is a memory. A previous processing data is somewhere stored and fed back. Because it has a memory and it has a cycle, it's very complex, and stability is a problem. Think about it, if your feedback is positive in nature, the output keep growing and growing bigger and bigger. Moment we have a feedback, stability is always an issue. It's been used for sequence predictions. For example, if you talk about a protein sequences, you want to predict what next amino acid is going to come, whether this particular sequence is going to be submerged or not. You can predict, if you are talking about what will be the next cycle, you can predict that. It has been used in language, it's also been used in control problems, control of dynamical system, identification of dynamical system, right? It's been used extensively in these applications. Now, let us look at what is learning. If you look at a standard definition of learning, the activity or a process which has been used to gain knowledge or a skill by studying, practicing, or being taught, or by experiencing something, right? That's the definition of learning. If I look at learning from the point of view of artificial neural network by Tom Mitchell, it's a computer program which is set to learn from its experience with respect to some specific task, let us say classification task or prediction task, to achieve certain performance, right? If the performance of the task T is measured by P, it tries to improve the performance by the experience. Experience comes from data. The more the data, better the performance is. That is why we call AI is data hungry. Not just data hungry, it is also computational hungry. When do we use this learning? Can I use artificial neural network for all problems? You can use it if you can't define explicit rules, right? A complex task which a human have to perform, right? But you can't explicitly write it out. For example, language models, you want to understand what others speak, or you want to understand the image, understand the context from it. That's a complex thing. It's very difficult to write it in an explicit rule. Whereas if you can just say, my acceleration is greater than so much, which means there is a crack. If you can identify an explicit rule, you don't really need artificial neural network to solve such task. But the environment is changing, even in the explicit rule, but the environment is not constant. It is changing with respect to time, changing with respect to domain. And in every domain, defining the rule is very difficult, and it's very difficult to identify in what domain it is present. In such cases, it makes more sense. For example, if you want to predict the financial market, right? Or if you are looking at autonomous driving, it's the most difficult problem. If all cars are autonomous, is much easier because every car will be running through rules. The moment human comes into picture, the intentions are different, the goals are different. That makes things more complex, right? So when the distribution is changes, what we call non-stationary data, that's when you really need to use artificial neural networks or learning based solutions. There are large data, very difficult to extract and keep the rules. There is a hidden patterns which I am not able to figure it out, right? There are financial transactions, historically I stored all the financial transactions of one particular shop. I want to find out the hidden information from there. I want to extract the relationship. I want to identify the anomaly, right? Identify a specific region, lesion region from medical images. It makes more sense. Personalization, recommendation systems, right? We talk about it. When a human expert is not available or use of human expert is not scalable, that's also a scenario where you will be using learning based solutions. But don't use it when you can clearly define a rules, right? So that's, and also where the data is biased, right? Whatever the collected data is biased even though you can't define explicit rules. So you have to be careful on when to use learning based solutions for different applications. Now let's look at history of learning, right? So timeline of artificial neural network, when it was started, what are the key milestones which led to different progress and where we are today, right? So I just talk about 1950 to 1960, that's when 1957 you have a perceptron algorithm came into picture. That's when McCulloch-Pitts model and all came in, they talked about we can represent logic gates, which is a very simple problem, and then perceptron came. Then multi-layer perceptron came. In 1969, Minsky talked about linear models. In 1980, the connectionism or foundational ideas came into picture. Then 83 comes a formal learning process in the timeline if you look at it, right? But if you see further from there, the backpropagation came in 1988, which changed the use of neural network for various tasks like classification and approximations. In 2000, there are quite a lot of applied AI came into picture. People started using a artificial neural network for various problems like health monitoring, compression, confinement, if you talk about concrete strength prediction, a structure health monitoring aspect of it. I'm just trying to give an example, right? So if you look at what is the life of, if you take a wood, if you cut, if you look at this section, from there you can predict what's a life, and when was the tree was planted and what's its current life, you can predict. They started using for remaining useful life predictions of engines, right? So a lot of application came. In 2010, because of invention of computing powers, the accelerations in electronics led to deep neural network. Multiple layers came into picture. Recently, if you look at VLM, vision language combined, generative AIs are making inroads into various applications, right? In a summary, in this lecture, we just talked about types of neural networks, different type of architecture, feed-forward feedback architecture, what is the advantage, disadvantage of them. We talked about learning, what's learning, when to use learning, in what scenario one can use, one should not use. We talked about feature extraction automatically by neural network, and we talked about history, timeline, of different inventions which leads to. In the next lecture, we will introduce types of learning, different types of learning, how the data will influence the learning, right, and that will help us to understand the basic building block in subsequent lecture. Thank you.